Hey guys, welcome to Great Learning. Now, boosting we use in the domain of machine learning to help us immensely. Now, I'm sure you're a person asking, saying, okay, so how is boosting, helping us in machine learning, right? Well, we're going to discuss all of that. In fact, we're going to discuss a lot more to give you a comprehensive understanding of these concepts. Now, ladies and gentlemen, we have a course specially made for these concepts because at the end of the day, when we're talking about ensemble methods and ensemble techniques of how we can work with machine learning to eventually find the best way to have a very efficient solution, boosting do play a very important role in that. And whenever you start your journey as a person who's into machine learning, once you clear all the fundamentals, once you clear all the basics, the next thing you'll be looking at is finding the best way to solve something, to solve a problem, right? There's many algorithms. There's tens of hundreds of algorithms that you can use in machine learning. Now, at the end of the day, how will you know which one to put where? How will you know what works well and what doesn't and all of that, right? So with the knowledge of boosting, you will not only find ways to effectively increase the efficiency of an already efficient process, but at the same time, you will also be a person who will now have the capabilities to actually dive right into the depths of machine learning, understand how it works, how we can make it better as a domain in itself, right? And that is so very important for us trying to create applications or us trying to solve some problems in this domain, right? So ladies and gentlemen, we here at Great Learning present to you this course on boosting. My name is Anirudh Rao, and without further ado, let's get started.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
Alright guys, so to come to the agenda of this particular course boosting, we're gonna have to take an introduction to understand certain concepts, right? Now I'm sure you've heard of these concepts. It's called bias, it's called variance, and all of these important terms, right? So we need to have a solid understanding, first of all, to know what bias is, to know what variance is, to understand what the change in these bias and variance will do to your machine learning algorithm and all of that. Right? So once we have a very solid understanding, I'm going to give you a lot of examples to make sure you guys understand that. We're going to be taking a look at understanding ensemble methods. Now, ensemble methods are a very critical part of machine learning. And if you've ever been to a machine learning engineer's interview or something like that, there's a very good chance you might be asked this term as well, right? So it's again a very trending concept. More than trending, it finds itself to be foundational, and a lot of people tend to skip it while learning, right? So we're going to be covering all of the really important stuff that you're going to require. Now, of course, after we are done with bias and variance and we've had a chance to understand ensemble methods, we're also going to be taking a look at bagging and boosting, which eventually is our discussion, right? So we're going to be diving right into the depths of bagging, understand what it is, how it works, and eventually doing the same for the concept of boosting as well. Now, one interesting thing I've always been asked is whenever I've had a chance to teach people bagging and boosting, at the end of the presentation, at the end of the seminar or whatever it is, they usually tend to be left a little more confused regarding, well, how does bagging compare to boosting in itself, right? So of course, I know after boosting, you guys might be wondering about the differences that exist between bagging and boosting. I'm going to be covering all of that for you guys as well. Right? So once we understand all of the important differences that lie in between bagging and boosting, we are actually going to take a look at a very small demo and understand how it is to work with these concepts. And eventually, ladies and gentlemen, we're going to be analyzing the results to a good amount of depth there as well, right? So all your theoretical learning plus all of your practical learning, I am sure, is going to give you guys an edge ahead in the domain of machine learning with this course, right? So guys, I hope the agenda is clear to all of you all, and I think it's high time we get started. Alright guys, so before we even come to the first item on the agenda, I just want to ask you guys if you knew this. Right? Now, consider a situation where you have the same data set, okay? Maybe the house pricing data set, the Boston housing data set, the Iris data set, anything that you want. You have one of your favorite data sets Do you know that you can actually use the same data set to actually work with multiple different algorithms to have multiple different results with multiple levels of efficiency, right? Accuracy. I'm sure you knew that, but did you also know that with the same set of data, the algorithms behave very, very differently. Sometimes the way they see the data in its most primitive state is actually very different. The way they try to match patterns in the data, the way they try to assess the structure that is hidden in the data is something which is very, very important. It is very common to think about saying, hey, I have certain data, I have a couple of algorithms, let me start feeding data into these algorithms and it should work, right? I mean, what's wrong in that? There's nothing wrong in that. The fact that you have to understand it is perceived very, very differently, right? So now when you actually give it a thought, right? If you talk to me in very complicated, extremely technical machine learning terms, I'll be more than happy to talk to you that way. But if you take the same data in the conversation and probably talk to someone who's not really into machine learning, into technical stuff, they'll not understand it, right? The way they would process that information would be very different than the way I would process it. Guess what happens in the case of algorithms and data as well, right? It is literally the same thing that happens. And for you as a learner, this becomes critical to understand, because in many cases before I've had a chance to teach bagging and boosting, the people usually ask saying, hey, so, since we have data, we have multiple algorithms, so we just pick up the best one and go about it. You can do that, but the vital thing you have to understand is, why does these algorithms behave differently? And of course, you can find out many mathematical and statistical reasons of why the algorithms behave differently. But what you are supposed to be answering is saying, okay, so if I have the same data, if I have multiple algorithms, how best can I make sure that I use my data to increase the efficiency of an already really well-working algorithm to, push it to fifth gear, to push it to overdrive, to make it want to perform a little bit better, right? I'll give an example. The same house price analysis that I was speaking about, right? It's basically a data set where it has all the details of the houses and the prices of those houses in a locality in Boston. That's the Boston housing data set. Based on various factors, you'll be able to judge why the house is priced so much, right? Think about it. You know, in whatever city that you are living in, there are certain areas and localities where probably land, plot, houses are extremely expensive, just because those areas are like really well furnished and all of that, right? So there are many ways of how price will vary for your house, and you can use multiple algorithms to actually go on to track that. And in this particular case, you can go on to use linear regression. KNN is very popular. Decision tree regression is extremely popular for these tasks as well. But one thing you would already know, since we already discussed this, is for the fact that when you run your data through run the same data through all these algorithms, each of them will give you a different accuracy score. It's not going to say, hey, I have 75% accuracy, and all three are not going to be 75. One can be 75, the other can be as high as 90, the other one can be as low as 60 or something like that, right? It's percentage. So you really have to understand why it happens, how best can you find the best algorithm, and how best can you even push the algorithm further to its importance, right? And that's where, when you start exploring machine learning into depths such as these, the concept of bias and variance will come into your picture, because these are very, very, very important concepts. And whenever you're talking about any sort of machine learning algorithm which gets processed into a machine learning model, these models will have biases and variance, right? So what is bias? What is variance? Don't think about machine learning terms for a second. Just think about bias in an actual conversation with a human being, right? When they say, hey, you're so biased, what do they mean? They say that, your intentions or maybe your thoughts are focused along only one train of thought, one focus path, and you're not looking at the bigger picture. So what happens when we're talking about randomness, right? Here's a really fun thing which you may not know in machine learning. Whenever you think about creating random data, when you say, hey computer, create random 10 numbers for me between 1 to 10, it's very easy for you to say, hey, it's just 10 numbers, it is random, and the computer is giving me something. But you have to understand that there was a formula that actually ran in the background to give you that random number, to give you that random ordering, right? So in depth, if you track it from the reverse path, you can actually create a mathematical equation which will lead you to the same exact order of your numbers coming out to be. So guess what? At the end of the day, it is not so random, right? Because it is biased. On the overall, it will be 10 numbers absolutely jumbled because you probably cannot find a pattern that's present there. But guess what? If you start hunting really deep into it, you will know what it is. Because even the most random data in today's world generated by a computer is biased to a certain extent. It's called random biasing, in fact, wherein you think it's random, but at the end of the day, your computer is following a couple of instructions to get to that point. So it's not really random completely, right? So in this case of machine learning, whenever we take out our data, right, how skewed is our data when you're considering complete randomness, right? When you say, hey, I want my data to be totally random, I don't want any sort of third party views in it, or I want to make sure that my data is untampered and it is 100% random. Bias comes into the picture and says, hey, stop right there, because at the end of the day, I know that there is a very good chance the data cannot be completely random, and here is why. That's the bias value, right? Now, let's talk about variance for a second. Variance, the answer literally lies in the name of the word itself, right? When you think about it, when you're talking about variance, why do we use variance? What does it mean by something is varying, right? So it's basically you have one point of comparison, and along those points of comparison, you say something is changing. For example, the light at the time of the day, right? Probably if you wake up at 5 a.m., you'll realize that the sun is not yet out. 6:30, the sun starts to come out. 7:30, it gets brighter. 12 p.m., 1 p.m., it gets extremely bright. And again, 6 p.m., 7 p.m., it just goes off, right? So the brightness in the sky is varying based upon the time. So the factor you're comparing it to is time. And what you have to understand is that there's something that changes. There's something that's varying. And guess what? You can track those varying points to a good amount of extent, right? This is really important for you to understand, because bias and variance will be different when you're working with different algorithms. And let me tell you, if you're a person who's thinking that, hey, will bias and variance have any sort of say on an algorithm that I'm working on, you'll be surprised to understand just by having these two metrics, just by tracking these two metrics, you can tell if your machine learning algorithm will function properly, or, will it mess up, or will it goof up in a couple of instances, right? So it's really important. Now, it's not just bias and variance. See, we're talking about these metrics which are helping us to measure certain errors, right? So basically, there's three types of prediction errors that you can work with. Bias, we already looked at. Variance, we already looked at. And the next thing, there's something called as irreducible error, right? An irreducible error, it's basically a tongue twister, right? Irreducible error. So basically, it's also called as noise. And if you're familiar with the concept of underfitting and overfitting, right? Overfitting is a situation where your machine learning algorithm is digging so deep into learning something that it is actually seeing noise rather than learning useful stuff. That's because it's hunting so much into the depths of your data, right? Think about it. Now, that is an irreducible error. And sometimes not all data is clean. Your data is going to come with certain stuff which will have absolutely no effect on your machine learning algorithm. That's the good case. The bad case is where your data will actually tend to mess up your machine learning algorithm more. You might think that, hey, it'll absolutely not hurt. One or two errors will not hurt in the data. But when your machine learning algorithm is learning, since it's learning from scratch, it's going to learn the wrong thing. Give it a thought, right? So it's very important that you understand these prediction errors, right? Now, bias, when we're talking about it in a machine learning term, it's nothing but an assumption that gets made by a model, which we're going to use to basically make the target function, our goal is to make the target function learn easier, and having an assumption thinking that our model might do this and eventually get to our results is something which is very critical, right? So the common train of thought you might have at the moment right now is saying, okay, so if bias is an assumption that's made on the model to see how faster it learns or something, models with high bias should work really well, correct? No, models with really high bias are actually less flexible, because at the end of the day, with a lot more biasing from your data, it's like lashback from your data, your machine learning model will not be able to fully learn from the training data to eventually tell you that during validation, right? So having high bias is not a good thing. Even though when you start out learning bias, it seems like a good thing. Absolutely not. Having high bias will eventually destroy your machine learning algorithms accuracy, right? Yes. I've been working on many cases where if you're not handling your bias and variance really well, it comes to a point where it will crash the entire accuracy of your model. Your model can go from 90% accuracy all the way to 65, and you'll be breaking your head wondering why this has happened. It's these, right? So it becomes very, very important. So what is optimal? If high bias is bad, what is good? Well, low bias is very, very good. In fact, it's actually preferred because whenever you have low bias, the models will basically fit the data points really, really well onto the regression line. And you have a regression line that goes on. You have multiple points that gets plotted around the regression line. That is how your machine learning algorithm learns, right? So when that is happening, you have to be very critical enough to assess and say, hey, having low bias will actually give my model the better of an ability to actually learn. That means it has a higher ability to learn and perform really, really well, right? So again, now if I ask you a question, so in machine learning, what do you prefer, low bias or high bias? Do you think you can give me an answer? Of course you can. It is low bias, right? That's the optimal situation. Thinking about variance. Now, variance is basically the amount of deviation in prediction whenever you're switching from one data set to another, right? So whenever you have one data set at hand, you'll be performing some predictions. You'll be defining how much of predictions that the model will do when you change from one data set to another set, right? So you're working on one data set, you plonk in another data set, you want to understand what is the variance, what is the change in your learning and all of that, right? So basically it is nothing but the estimate of the target function, and you'll be understanding and you'll be tracking how the target function will change whenever you use what? You use different training data. Now, ladies and gentlemen, this is very, very important for all of you all to understand on the concept of variance. Right? So now that you know bias, now that you know a bit of variance, you might be a person saying, okay, so what's good in variance? Do we have high variance? Do we have low variance, or what? Guess what? Any machine learning model, or I want to say most of the machine learning models, is going to perform slightly poorly on the data that it has never ever seen before, right? That's the entire purpose of us trying to use the training data, eventually later use the testing data and all of that, right? So what we want to do is we want to have a model with low variance, right? As it is with low variance, you'll have models perform poorly on data it has never seen before. Imagine it with high variance, right? High variance will not give clarity to the machine learning model. It will not know what it has to learn for. And think of high variance with high bias or something like that, right? Your machine learning algorithm is absolutely confused, and at the end of the day, instead of giving you something like 75-80% accuracy, it's going to give you 50% accuracy, and we don't want that, right? So that's important for you to understand. So you might be a person asking a question right now saying, hey, we know that high bias is bad. We know probably high variance is bad, but is there a trade-off? Is there a balance between bias and variance? Well, yes, there is. It's called as the bias variance trade-off. What happens is that this happens in the real world as well. Once you start decreasing one, the other one starts increasing, right? You tend to decrease bias. That's when your variance goes up. You increase variance. That's when your bias goes down, right? It works both ways. Increase bias, variance goes down, increase variance, bias goes down. So since it's interlinked with each other, this is called as a trade-off. Now, in this situation, what you should be looking for is the best of both worlds. Having very good biasing while having a decent enough trade-off such that your variance values are also working for you. Right now, it's like a balance. It's like literally a weighing scale with two weights. You have to find the best way to balance, right? You might say, hey, I really don't care about variance, so I'm going to have really low bias. It means you're going to have really high variance, and that's going to cause you a lot of trouble at the end, right? So you don't want that. You have to really understand that part about the prediction error as well, right? So ladies and gentlemen, at this point of time, we had a chance to take a look at variance. We had a chance to take a look at bias. We understood what they are. We understood how they affect the machine learning models. And we also understood what happens if you start changing each one of them and how your machine learning models are going to react as well, right? So I hope we are clear with everything that's covered in that section. Now, the next section, we're going to be discussing something called as Ensemble Methods. And I'm very sure you might have heard of the term very vaguely, even if you're new to machine learning. Ensemble Methods, Ensemble Techniques. What are they? Well, let me tell you this. The general principle of what an ensemble method in machine learning is basically to, when you say ensemble, you're trying to assemble a lot of different things. Here, what you're trying to do here is you're trying to assemble multiple machine learning models to actually work in unison, right? So instead of just having one data point, one machine learning algorithm work on it, what you're going to do is you're going to use the same data point and eventually have multiple algorithms work on it, right? Once you use the power of several models to work together on a data set, you can have a choice. You can come to a situation where you combine the learning of all of these different models to give you one really big fat machine learning model, which will work way better than all of these individual units combined, right? Think about think about the military, for example. If it's just one soldier marching into battle, well, yeah. But then if you have 10-15 people, things might change. If you have 100 people, it's fantastic. If you have a battalion, wow. If you have an entire army worth millions of people, it's way better than that one guy, right? Maybe in a spy situation, the one guy is better than the millions, but in a generic military situation, the million guys are way better than just one guy, right? Similarly here as well, in these ensemble methods, once we start bringing together the power of what everything and everyone, in this case machine learning models, have learned, we can use the learning to eventually have things to work better for us, right? And ensemble methods are very, very important part. In fact, these are what make up bagging and boosting. These are divided into two groups. Basically, they're called as parallel ensemble methods and they're called as sequential ensemble methods. So what are they? How do they work? Let's take a look at them, right? Well, parallel ensemble methods basically, you have certain learners called as the base learners. These base learners use the data to actually run through it, assess, perform all their validations and work as it is. These are base learners who are just there to make sure that, you have a number to compare to, you have a metric to take a look at, right? So it might be slightly confusing for you to understand. So let me quickly give you an example. Think about a situation where, you might be deciding that you want to watch a movie. So what do you do when you decide you want to watch a movie? Probably you go to WhatsApp, you go to Instagram, you text a couple of people saying, hey, do you have any suggestions to watch a movie, that I want to watch a movie for this particular Saturday or something like that, right? So what will you do? Probably you'll have 5 or 6 movies, and if there's something which is like really, really trending, I think at the moment it's Money Heist, right? So when something like that is extremely trending, you will know, people will talk about it. Out of 3 guys, maybe 2 guys say, hey, you have to watch that TV show. What are you going to do? Eventually you come home and you watch that, right? So you ask multiple people for their suggestions, you analyze their solutions, and eventually figured out what needs to be done. You're sitting and watching your favorite movie show. Wow, that sounds like such an analytical process for you turning on your TV and watching Netflix, right? But yes, this is how parallel ensemble methods work. Now consider the situation of the sequential ensemble methods. Sequential ensemble methods, what it does is, instead of having all the base learners learn the same thing, here you will have the base learners actually learn sequentially. When I say sequentially, I mean one alongside the other with all of the early learners, where we're trying to basically get the models to work, right? So instead of just having one dude work on one model, instead of basically one data point working with one algorithm to create one machine learning model, you're going to have these initial learners, they call as the base learners, and after that comes the early learners. And once you start working with all of these unison, you can take the data from multiple algorithms, analyze the data, see what the error rate is, and try to see if you can basically bring down the net error rate when you combine everything else. If you can do that, it means that when you're working together with all of your accuracies, your model can perform better than just with one algorithm, right? So if you can boost the overall performance by, boosting and doing a couple of changes and getting more than one algorithm to work at the same time, would you say no to that? Absolutely not. No one would, right? So that's sequential ensemble methods for you. Now let's quickly discuss a little bit more on ensemble methods, right? So in generic cases, in most of these cases, what happens is that most ensemble learners basically use a single base learning algorithm, and this eventual base learning algorithm is used to produce multiple other learners, and these learners are called as the base learners. And once these base learners are out there, we will know that they can be learners of the same type, which will eventually lead to common homogeneous ensemble, right? So basically a common homogeneous ensemble is a situation where you have one algorithm producing similar algorithms, which at the end of the day have the capability to work on the same data to give you an overall increased efficiency of your machine learning model. That's a very complicated sentence, but I'm sure you understood that, right? So in real world, in the domain of machine learning, to speak technically, random forests use parallel ensemble methods, and basically the concept of AdaBoost. I'm very sure you must have heard of AdaBoost or AdaBoost as it's called. This uses sequential ensemble methods, right? So random forest parallel ensemble methods, AdaBoost sequential ensemble methods. Now, if you're learning, if you've taken up this course, since you're preparing for a machine learning engineer's interview or something, remember this, because there's a very good chance the interviewer might pop you a random question in the middle of the interview and say, hey, can you give me an example of sequential ensemble learning? And at that time, we don't want you to go blank. We don't want you to think about what ensemble is, what the examples are, right? So I hope with this, you can take a note of it, and it's very important and that you will answer when you're asked about this, right? So it's not always homogeneous learning. It's not always one learner adding on to everything the other learners have added and eventually give you a result. There are cases where you will have heterogeneous learners. Heterogeneous learners are, you have one data point. These eventually will start looking at different entities, different data points compared to each other. And if each of those detections are accurate on their own, what happens to the overall result? The overall result is also more accurate, right? So for ensemble methods to actually be more accurate than just one of these learners that they use, the base learners, the first learners that go in to actually give you all the other models and work with all the other data, right? This has to be very, very accurate. This has to be very diverse. So it's not like you have one algorithm, just send any random algorithm, get it to create hundreds of it, you have a better output. No, your base algorithm, your actual algorithm where you are calling the base learners, this has to be very critically managed, critically controlled, right? So this is something which is very, very important for you guys to understand.
So in this video, we are going to learn about boosting algorithms. So I personally would say that boosting algorithms are actually gift to any particular data scientist or a data field. Because when you use the traditional algorithms, it is a bit difficult to get the proper accuracy what you are expecting. But using the boosting algorithms, we can easily get the best accuracy and the best optimized result as the solution. So let us discuss what are the boosting algorithms, and we will also discuss how to fit such algorithms on any given data set. So once you deal with a data set in the industry, you can use the boosting algorithms to optimize the solution and give the proper result. So firstly, I am going to start with understanding or the definition of boosting algorithm. So I'll be starting with what is boosting algorithm. Let us understand that. So boosting is a supervised machine learning algorithm. So basically supervised machine learning algorithm, we all by now, we know that what is a supervised algorithm, which follows ensemble techniques. So what is that? Ensemble technique or the rule of converting a weak learners to strong learners by reducing the bias and the variance in the model. So basically we all know that to a model or for any model to be called as the generic model or the general model, we actually need to reduce the bias and the variance. And we also know that there should be always a trade-off between the bias and the variance. Then only we can say the model is generic. So the output given by the model train is actually same which is on the unseen data. Okay, so this is about the bias variance trade-off. How to achieve that very precisely? You can use the ensemble techniques. So let me give a gist of how ensemble techniques actually works. So basically, let's say you have a data set. So let's say from the data set, usually in the traditional method, what we will do is that we will build one model and we'll take the output. But in the ensemble techniques, we will take output from different models, which is built parallelly or sequentially. So basically this is the order how your model is built. So you have different models here, model 1, model 2, and this is model 3, and you will take the output from all the models and finally you will give the output. Okay, so basically ensemble technique is the combination of different base models and finally you will give the output. So this is about the ensemble technique and the boosting algorithm. So now let us go and understand on fitting this model on a particular data set. So I'm using a particular data set to understand or fit a model. So I'm using the iris.csv. So this is the CSV, that is comma separated value or the data set that I'm having. So let me just walk through this data set. So this data set has got ID, sepal length, sepal width, petal length, petal width, and the species. So basically this is the biological measurement of any flower. So there is a flower called as the iris flower, and basically based on the sepal length, sepal width, petal length, and the petal width, we are going to classify them as a different classes. So if we look at here, we have three different classes basically: iris setosa, versicolor, and the virginica. So this is the classification problem. Based on all these values, your model should be able to classify your flower as iris setosa, either virginica or versicolor, or the three different multi-classes. So this is a particular data set. So I have all the numeric values. I have one particular categorical value. We are going to encode it. We will see about it now. So let us just come back to the notebook here. So I'll start running this particular code. So basically, firstly, I'm importing all the essential libraries for the analysis. So next, I'm going to read the CSV file. So I'm reading it as the iris. Then after we all know that before building any model, we should also make sure that data is very well pre-processed to fit such models. So if you have the categorical data or the data is not in range, the output is given from your model is not so up to the mark. Okay, so you should always make sure that your model is giving the precise result, so that you need to understand the data, explore the data. That's what we say, exploratory data analysis. Also, you need to pre-process the data. This is a very important step in building a model. So I'm going to start with a basic data checks. So basically we all know that head function will give you the first 5 rows. So I'm just looking into the first 5 rows, either just to check whether a data set is read properly. Next, I'm going to look into the shape of the data set. So basically I have 150 rows and 6 columns. Okay. Next, I'll just run this. So basically now what am I doing? I'm just understanding what are the columns I have. I have ID, as I mentioned, sepal length, sepal width, petal width, species as our target variable. Basically ID, sepal length, sepal width, petal length, and the petal width, these are all the independent variables, whereas your species is the target or the dependent variable. Using all these things, you are going to actually classify the particular flower into different classes which is present in the species. So next you are going to understand the info. Info basically will give you the complete information about the data set. So you can see 150 entries, 150 rows, index from 0 to 149. Then basically you have all the columns which is numerical except one which is object type. So next we will understand the description of your data. So basically what description will help you? Description, we all know that it will give you the statistical information of the data. So why it is important? Just to know how your data is distributed. So the moment you get this, you have to check whether what is the minimum value. You can say what is the standard deviation. That means how consistent is your data. Next you can see the mean value. And you should also go and see a mean and median should be in the range. So it will help you to have the knowledge about normal distribution. By now we all know that normal distribution means the one which is having the mean and median is same. So just to understand there is no skewness in the data. So mean and median for this variable is fine. This is also fine. This is a bit skewed, but that's fine. Okay, so this is fine. So basically you will understand the distribution of the data. So this is the sepal length of the sepal. Basically the description, as I mentioned, length of the sepal, and this measurement is in centimeter. Petal length, width actually of the sepal, length of the sepal, that is length of the petal, width of the petal, all of these measurements are in centimeter. then the species name, then ID is nothing but the index. Okay, that is what index number or the ID, that is a unique ID. So next, what am I doing? Very importantly, just we have to understand what are the columns that we need to have. See, just because your data have so many columns, it doesn't mean that you should always involve all these columns into your model. It will cause a dimensionality problem. Okay, the computationality is very high. So you should come and you should always drop the variables which is not important for the prediction, right? So which is not having a proper variance, I can see. So basically I am dropping the ID column here. Why? Because ID will not help me to classify the classes, so I don't need ID. Since ID will not explain any type of the correlation towards the target, I can drop it. So after that, I'm going to find how many classes are there, or what is the distribution of data in each classes. Okay, so I'm using the value underscore count function. So if you see, so what does this mean? Iris versicolor has got 50 data points. Totally we have 150 data points. Okay, 150 rows. In that, Iris versicolor has got 50. Virginica also has got 50 data points, and Setosa has got 50 data points. So what does that mean? It means that your data is balanced data set. So what is the meaning of balanced data set? So the data set is well balanced or equally distributed between all the classes. So let me just give one particular example here. Let's say based on some values, you need to classify a particular fruit into apple or mango. Okay, let's say in your data set you have 50 apples and 50 mango. That means you can say that it is balanced. That means your data is balanced and your model output will be very well. Let's say you have around 70 apples and just 30 mango. So model will have a biased result towards apple. So when you have the unbalanced or imbalanced data set, you should always do some imbalanced treatment. Okay, so luckily we don't have the imbalanced data set here, but in the industry you will definitely have the imbalanced data set. You need to treat that further. So each class has the equal data points, so I don't have any problem with this, so that we are good to go. So next, so this is the basic checks about the data. So how data is distributed, what data is telling, what are the columns, what are the rows, how many classes are there. So these are all very important to understand the data set. So next, let us understand the exploratory data analysis. That means explore the data even more. So the first step in this is data cleaning. So always remember garbage in, garbage out. That means you should always have the data set which is actually cleaned, well cleaned, or it should not have any sort of the null values in your data. So there is a function called isNull, and I am summing up all the null values. So isNull is a boolean. It will give you the boolean output as true or false, and I am summing up all the true false values here. So if I run this, I could see there is no null values in the data. That means your data is clean enough. Okay. So after that, we have the data visualization, just to visualize how your data is distributed. So basically I am using the scatter plot here. So I'll just walk you through this code. So basically I am using the species for different species. I am plotting the scatter plot. Okay. So here it is Iris setosa, and I am plotting the scatter plot, and for the x-axis I have the sepal length, sepal width, and I also have the color, different colors. I can give the colors and the label accordingly. So similarly for the versicolor I have the same, and Virginica, and I am plotting the scatter plot as it is. So why am I using the scatter plot? Why is it very important? So scatter plot is very helpful in order to understand the correlation between any two variables. Okay, so now I want to understand the correlation between the sepal length and the sepal width. So basically for different classes. So for the setosa I have red color. So these are all the setosa flowers which is distributed. So versicolor, I have this blue color, and a virginica is this. So basically the distribution of your versicolor and the virginica is kind of mixed. That means they both have a similar, I mean in between or any similar values. So by looking at this plot, I can say that your sepal length and the sepal width is very well correlated or positively correlated in the case of setosa. And setosa or the small flowers, if you look at the sepal length and the sepal width, it comes under the small flowers compared to virginica and versicolor. Versicolor has the highest sepal length, so you can say the virginica is bigger flower in size. So for setosa, it is very well explained. Okay, so sepal length versus sepal width. Setosa has got the proper positive correlation in their sepal is smaller than the virginica and versicolor. So this is what the analysis that we found here. So next, similarly, I am going to have the petal feature. So first I have seen how your data or the correlation is distributed in case of the sepal dimensions. Next I am going to look for the petal dimensions. So next we have is the petal dimensions, as I mentioned. So I'm using the same code, just I have to vary the x-axis, that is what the petal length, and y-axis is the petal width. So this is for the iris setosa. That means I'm going to compare how the correlation is working with the petal length and the petal width. Is there any kind of pattern or the positive or negative correlation with this? So if we actually look at this, this is petal length versus petal width. So you can see it is very well correlated. So here you can see a cluster of flowers. This is actually the setosa. So we have a kind of slightly positive correlation. So if you see the versicolor, also there is small merge between these two, but it's actually okay. So intersections, but it is also positively correlated, and virginica is not well positively correlated, but I could see the distributor. So basically here also we can see the petal has classified the difference much larger than sepals, right? So in order to see which type of flowers and how to differentiate these things, so better than sepal length, your petal dimensions or petal length and the petal width is actually explaining the separation or the separation between the classes really very well. So next we are going to understand the violin plot. So in this we will see the distribution of the data, and also we will see how your data is distributed towards the median point. So basically here I am using the subplots. So we all know that how the subplot works. Basically if you want to plot the different plots at one particular go or one go, you can use the subplots. So here also I am using, first I am using the petal length. Okay, so and I am taking all the species. So just to see how individual variables are working here. So I could see this is the setosa, this is its distribution petal length, and next after that you have versicolor. See, just after virginica, which is having the less petal length, maybe the maximum of 2. After that you have maximum of maybe 5.5 with the versicolor. So next you have the virginica. Similarly, petal width, you can see the setosa is the smaller flowers. But if you take the sepal length here, sepal length is not dividing all these flower very well. That means the end point here you can see end point of this is starting point of other flower. In the sense there is no much intersection between the data points. But if you see the sepal length, there is a much intersection between the data points, especially if you see this and also these things. Sepal width is not at all classifying your data points well. So keep in mind, so petal values are really very useful. Okay, so by using this analysis, these plots, we can understand that petal dimensions like petal length and the petal width are very important variables in order to classify the classes. Okay, so that's it. So next, the violin plot, what does it do? It shows the density of the length and the width in the species. So how dense it is, okay? So the thinner part denotes that there is a less density, especially here. This thinner part means there is a less density. Obviously, we all know that it is of course a normally distributed. That means the values are much distributed towards the median or the mean, right? So that is the greater or the big idea. So after that, we are going to understand whether there is an outlier in the data or not. So by now we all know that what is the outlier. Any value which is out of the range is particularly called as the outlier. And why it is very helpful to see those? Because it will give you the biased result. Okay, so it will really affect your particular model, whatever you're going to build. So just to understand, especially if you're building a statistical model, always remove the outliers. So here basically I'm not building a statistical model, it is tree models. So I'm using the box plot. We all know that box plot is a plot which will help you to identify the outliers in the data. So any points after the whiskers will help you to understand these are all the outliers. So basically if you see with iris setosa, there is much more outlier. Not so much, but there is an outlier bit in the iris versicolor in the petal length. So the outlier is very less. With the virginica, there is no outlier at all. So what is analysis? Outlier in the petal length for the iris setosa. So now I can see there is some outliers in the iris setosa with respect to the petal length. Similarly, I could see for the petal width. So there is a few outliers here. And similarly, I could see for the sepal length, there is again very few negligible outliers, and also this is also negligible. So finally, what I can do is that instead of doing outlier mapping or outlier removal, I can just carry that because it is very negligible when compared to those data points. So you can see very one or two or very one data point which is having the outlier, that is actually fine. So I'm not doing any kind of outlier treatment here. I'm directly moving into understanding the correlation. Okay. So basically now I'm plotting the heat map. We all know that heat map will help you to have the correlation matrix. Okay. So it will help you to have the correlation values for each variable. So you can compare all the independent variable with the dependent variable. You can either go for the pair plot just to understand the correlation, or if you want a value, you can go for the heat map. So I'm just calling iris.core. So iris is the data set, and .core basically which will help you to have the correlation, and not means so it will give you this box shaped structure and also the values. And this is the basically structure or any particular palette I'm using. And so now if you could see here, so basically this is the id I'm ignoring at a point because I'm not using id, so I have dropped it. So sepal length. Okay, so here the sepal length with the sepal length has got the 1, but if you see the analysis, so we can see the correlation between the sepal length and the width is very less. So why? Because we have already seen there is so many intersection and it is not explaining the target variable very well. So again the correlation is very less with the sepal values. Okay. So whereas that is point just 11, but with the petals it is actually very high. When you take the petal length versus petal width, you can see it is 0.96 basically. Okay. So petal variables are very important to classify the classes. So also it is also another way of understanding which variable is important. Now we can see that these petal variables are very important in order to classify the classes. So once we understand the data and once we have that particular hypothesis that which variable is important and why, next we can go for the data pre-processing basically. So what is the data pre-processing? So just to pre-process the data, make it model ready. Okay, so that is called a data pre-processing. So here converting all the categorical variable to numerical. So the first method that we follow here is converting all the categorical variables into numerical. Why? Because your model cannot read the categorical variable since it is a string. Okay, so it cannot differentiate the classes the way humans do. So that's why I need to convert. So basically I'm converting For that, I am using the label encoder. So why? Somebody can think why there is a label encoder instead of using the one-hot encoding. Why? Because label encoder is ordinal. So why it should be ordinal? So as I already mentioned, Iris setosa flowers is smaller than Virginica. Virginica is actually smaller than versicolor, right? Or the other way around, my bad. So setosa is smaller than versicolor and versicolor is smaller than Virginica. So in order to have that order, you need to always go for the label encoder. So when to use the label encoder, I guess you're all clear by now. So label encoder can be used whenever you follow some order in the classes. Okay, so then you can go for the label encoder. So it will help you to assign accordingly. That means it will assign 0, 1, 2. So we all know that 0 is less than 1, 1 is less than 2. Okay, so such kind of encoding you can use it for the points wherever it is ordinally nature. That means it follows some order. So here I'm going to run this particular chunk of the data. So basically if you see, so I'm using from the sklearn, I'm importing the pre-processing. There is already a library for that, and I'm calling the label encoder. Okay, so this is what from the pre-processing I'm using the label encoder, not the one-hot encoder, because here your classes follows the order. Then I'm passing the species to it. So it will classify or it will transform this particular into 0, 1, 2. That means 0 refers to setosa, 1 refers to versicolor and 2 refers to virginica according to its ordinality. Okay, so next is nothing but the model building. So let us go and understand how to start with the model building. Once you complete the pre-processing, exploratory data analysis and analyze the data, so the next step is when you start the model building, you always know you need to split the data into training and testing. So here I am going to firstly import all the important libraries. So I'll walk through one by one. So one is from the model selection, train and test split. So this will help you to split the data set into training and testing. We all know that we'll always keep the major part as a training to train your model and few unseen data to check your model whether your model is performing well or not. So next is what the k-fold cross validation. So I'm using this because I'm using the grid search CV. Okay, so then cross validation score. I need to understand how my model is performing. Label encoder, I have already used it. So decision tree classifier. So why decision tree classifier? Because we need to create a weak learner. Okay, so what is the meaning of weak learner? So, and here I am using the decision tree as the base model. As I mentioned, Ensemble Techniques is a combination of different models and providing the result. Here I am using the base model as the decision tree. Okay, so how to prepare that? So basically, what is a weak decision tree? So the decision tree which has got just one node, each node represents some sort of the rule, is it? So that just has got one node and only 2 leaves. Okay, it just has got only one split. Okay, so basically with just one. So these are also called as the stumps. So they are not eligible enough or they are not capable enough to explain all the variables properly, right? Let me give an example. I want to classify the given person as diabetic or not. Okay. So firstly, I'll make a rule. So I'll say that age as one variable. So if the age is less than maybe 30, I'm making the rule. If it is yes, then I will say that the person is not diabetic. Is not diabetic. Else I'll just classify the person as diabetic. Okay. So can you imagine that just by looking at one particular rule, I cannot say that the person is diabetic or not. Sometimes, even though age is greater than 30, the person might come to the non-diabetic category. So with just one rule, your model will fail to explain. It has got so much bias. So there is no proper result coming from the model. Again, there is another set of weak learners. So basically, what is that? So those weak learners which is having the higher variance, like it is having so much rules, so that whenever there is unseen data, your model will get confused and your output will be less. So basically, I am using this particular decision tree as my weak learner. Okay, so as the base learner, base model, I'll combine different stumps together and provide the result. Okay, so this is about the base learner, and from the ensemble I'm calling the AdaBoost classifier. As I mentioned, in the ensemble we have AdaBoost, gradient boost and XGBoost are the different classifiers. So I'm calling the AdaBoost classifier. By now you're all aware of how AdaBoost algorithm works. So next is what the gradient boosting classifier I'm calling it, and confusion matrix, which is very important to see whether your model is classifying the result properly or not. So next I'll just run this. So next is what, after getting all the important libraries, then you need to split the data for training and the testing. So I'm taking 80% for the training and remaining 20% as a testing. So I'll run this. So basically I'm looking at the shape of the training. So you can see the training has got 120 and 4 and the testing has got this much. Okay, so this is for the testing x variable, and there is for the y, there is only one target. This is y, this is x basically. Okay, so I'm going to start with building the base learner. As I mentioned, here AdaBoost algorithm will take the base learners all together, combine sequentially until it gives the proper output, until there is no misclassification. So let me just draw a small diagram about it. So basically, how does your AdaBoost classifier works? So let's say AdaBoost. So it will take many different weak learners. Basically, these weak learners are decision tree 1, 2, decision tree 3, like this. So basically, what your AdaBoost algorithm work, we all know that it is sequential. So it will take the result of the first algorithm and it will assign the higher weight to the misclassified point, and it will again feed back into the next algorithm. Again, here it will take the output, okay, from this and assign the higher weight to the misclassified point, because it should not get misclassified in the third algorithm. So similarly like this, basically it will finally stops at the moment, or it will finally end providing all the data points which are very well classified. Okay, so this is about the AdaBoost algorithm. How does it work on a brief? So now I'm going to build a decision tree first. So here I'm calling it as the shallow tree. This is the decision tree. I'm calling the decision tree classifier, and I'm giving the maximum depth 2. Why 2? Because it's just a stump. So I'm building a weak learner. So you cannot give so many depth to it. Depth in the sense only 2 nodes. Okay, so I'm just taking the 2 nodes or only 1 node with 2 leaves, and the random state of 100. So each time I'm picking just 100 data points. Okay, so I'll run this. So now I have used the decision tree classifier. Next I'm going to fit training, a particular training variables or the training data to those trees, and next I'm going to predict the y actually by using the test, and I am going to look at the accuracy. So basically, if you look at the accuracy, it is 93%. Okay, you might think, okay, since it is giving the good accuracy, but when you give the another unseen data, your model will absolutely fail. Okay, so why? Because your model does not have a proper rule or enough rule to classify the data points. So if you look at the confusion matrix, you can see there is again a misclassification here. Okay, so apart from this, there is again the misclassification here. So next, what am I starting with? I'm going to start with the ensemble techniques. So now let us discuss how does the boosting algorithm works. So what I'll do, I'll just give some example. With some example, I can explain how does the boosting algorithm works. So as I already mentioned, boosting algorithms or any type of the ensemble method takes the multiple base learners and to make them as the strong learners by reducing the bias as well as the variance. But how exactly the boosting works? So let's say we have multiple base learners here. So let's say I'm using the first base learner base model M1. Then let's say the second base model M2. The third base model, that is M3, like this. Let's say we have n number of base models. So again, let's see how this n affects your boosting output. So now let's say, for example, you have a data set. So basically, this data set is first given randomly. It is sampled and given to the first model. And obviously you'll get an output from this model. Let's say this is the classification problem. Like basically your model should classify the output based on the classes. And of course there might be some misclassification because it is a weak learner, right? So since there is a misclassification, that particularly misclassification data points, let's say for example these three are the misclassified data points. These three data points are given with a more weightage or more coefficient. Why? Because see, we all know that whatever the data points that we are assigning to it has its own weight, right? So based on the weight, okay, so now what we are doing, that basis we are giving more weight to these misclassified points and we are sending back again to the second model. And boosting is a sequential technique. Okay, so here again these three are given with the more weight. Why? Because the second model should concentrate more on these three misclassified points. Again, it will give some output. There might be some misclassification. Let's say there is just two misclassification. These two data points are again given with the more weightage. We are assigning some weight to these two, updating or upgrading the weight, and then again it is given to the third model. Okay, let's say the third model output has got only one misclassification. Again, this is given with more weight to the next model. So until when you are going to do this weight or you are going to upgrade the weight, until you get there is no misclassification or a complete very less misclassification from your model output. So finally you will get the output in which all the data points are classified well. Okay, and also it will be having the very good accuracy. So this process, so basically it takes the data which is having its own weight as a coefficient, we all know that, and each data points will be assigned its to the more weightage, those who have misclassified from the first model, that is given to the second model with the more weightage. Again the second model misclassified data points is given with a more weight, something like this. Okay, so no matter whatever the mispredicted points are given with a more weightage, finally you will get the output with all the data points are exactly classified perfectly and also with the highest accuracy. So isn't it amazing? I mean, you can easily see that how you're taking just a weak learner and making it as a strong predictor at the end. This is the AdaBoost technique, or any boosting algorithm exactly works like this. Okay, so there are different types of the boosting algorithms like AdaBoost, gradient boost, and as well as there is a XGBoosting. So we will discuss each one by one. How does each particular algorithm vary in its functionality and which is exactly better? Okay, so now I hope you are all understanding this. So now let us go with the definition. So I have given the definition. Boosting gets the multiple learners. As we know, it is ensemble technique. The data samples are varied and therefore some of them may take a part in the new sets more often. Okay, so in each iteration, this is the main point, the data points which are mispredicted or misclassified are identified and their weights are increased so that the next learners pay extra attention to get them right. Okay, so during training, algorithm allocates weights to each resulting model. As I mentioned, each misclassified points are allocated with a particular weights during its training. A learner with a good prediction results on training data will assign and the higher weight than a poor one. Okay, so you're assigning the more weight. So when evaluating a new learner, so basically boosting also needs to keep track of learner errors. So basically, so when again and again, so there is again the learning rate. Okay, so at what rate you need to assign the weight, at what rate there should be an iteration, etc. So all these things we will discuss under the parameters that is related to the boosting algorithms, particular boosting algorithms. So now let us see why exactly boosting is very effective. So, ensemble methods in general increase the stability and performance of machine learning models by eliminating dependency of single estimator. So, as I mentioned, there are multiple estimators which will give you the output, which is more and much more efficient than the single predictor. Okay. So, next we will discuss about the AdaBoost classifier. So, as I mentioned, we have different types of the boosting algorithm. So, I am going to start with the first type of the classifier, that is AdaBoost Classifier. So, you can also call it as the adaptive boosting. AdaBoost is also called as the adaptive boosting. So, a AdaBoost classifier uses original dataset to fit the classifier and then adjust the incorrectly classified weights by fitting the additional copies of same classifier. So basically, AdaBoost works exactly as I mentioned now. So it will take the unclassified or misclassified or mispredicted data point, assigns with a more weight, and it passes to the next model with some learning rate. Again, it will do the same thing. Okay. So this process will continue until your AdaBoost algorithm classify the whole data set properly and you got the best accuracy. And also you can see the best confusion matrix, which is having all the true values are right, and also the AUC score. Okay. So next we will learn about AdaBoost classifier. So I have already imported the library here. I have already called the AdaBoost classifier. This is sklearn. So I'm just assigning the classifier to some variable called ABC. Okay. So AdaBoost classifier has got some of the parameters or the arguments which is inside the bracket. Let me go and explain what exactly each one of this. Okay. So first I'll run this particular line of code. So here what am I fitting? I am calling ABC, which is AdaBoost classifier. Instead of just calling this, I'm just making the variable there. Now let us discuss what are the important parameters should be there while classifier. Okay. So as we already know that there are some hyperparameter tuning that we have to do in future in order to get the best result. Right. So in order to improvise a result, you need to always add the hyperparameter tuning. Okay. So now we will discuss about it. So the first hyperparameter is n parameters. Okay. So what are this n parameters? Number of estimators. Sorry, n estimators. It's not parameter. So the first hyperparameter is n estimator. Number of estimators that you are going to use. Okay. Let me go and explain what is the meaning of that number of base learners basically. Let's say for example, I'm just using only one base learner. Instead of 50, let's say I'm just making it as 1. Can you imagine the result? Obviously, the result will be not good. Why? Because it is having just one base learner to predict, right? So your result will obviously not a good one. Let's say 2, 3. So how do you decide this particularly? Based on this only your result will be decided, right? Let's say for example, I'll make it 2. But still, just a 2 estimators will not give you the accurate result. There might be a lot of misclassification. So first I'm going to trial with a 50 n estimators. That means number of estimators. I'm giving 50. That means 50 such base models. Okay. So number of estimators used to build the classifier. So firstly I'm giving 50. Let's say for example you will give 1000. Okay. Can you imagine how computationally high it is? Because it is an iterative process. Always remember your boosting algorithms or any type of the optimization technique is iterative process. It will go and find the best output. So once there is a model which classifies your data point properly, after that it will just run the iteration. So it is computationally, space computationally, it is very high and it is time consuming. So always have a parameter which will give you the best result. Okay, we also have the parameter search for that, that is a grid search CV, random search CV. This is all the optimization techniques. So firstly, I'm giving just a 50 as a default n estimators here. Okay. So next is what the learning rate. What is this learning rate? Learning rate is nothing but at what particular step each iteration should work. So I'm giving the learning rate as 1. So if you give the learning rate more, there might be more misclassification because your model will learn at the higher learning rate. Again, this is optimization. Okay. So next, the base estimator here I am giving is the shallow decision tree. See guys, like you can fit this particular AdaBoost algorithm or any type of base learners. Okay, so there is no restriction that you should always take decision tree, but we always use the decision tree as a base learners even in the industry. If you go also, you can see random state 1. So random sample is like random state is 1. Okay, so this is about it. So learning rate is nothing but weight applied to each classifier. Okay, at what rate the weight should be applied, at what rate the iteration should be run. Okay, so a higher learning rate increases the contribution of each classifier. Okay, so as I mentioned, there is always a trade-off. As I mentioned, you cannot exceed a particular point, then your model will not give the proper output, and you cannot also keep a very less so that your model contribution won't be that good. So you should always have the trade-off in the learning rate. Okay. So next is again, even in the n estimators, you should always have the trade-off. How much estimators that you need to use. So these two are a very important parameters that you can tune in order to improve your result. That is what we can do in the hyperparameter tuning. So next is what the base estimator. So I'm using the base estimator as the shallow tree here, which is a weak learner. We all know that. Random state controls the random seed given at each base estimator, at each boosting iteration. So it just controls how many random data points or how many random seed that should be given at each particular model level. Okay. So this is exactly about AdaBoost algorithm. So I'm using the AdaBoost classifier. You also have the AdaBoost regressor for the regression problem. So always remember this type of algorithms with you can use it for also classifier or as well as a regressor. So next, I'm going to fit the AdaBoost classifier here on my training data set. So basically I have training. So I'm fitting on the training data set. If I run this, I could see it is fitted on the training data set. So ABC is the AdaBoost classifier that I assigned, and I am using the dot fit function in order to fit this particular algorithm on the training data set. So next what I am doing is that I am giving YABC. That means once I train the model, I need to test the model. What is the accuracy, right? So I am giving the unseen data in order to predict the Y. Okay, so that is what I am doing. I will run this. So YABC is a variable in which I am predicting the test values. Okay, so after this what I'll do, I'll run the score. I just want to see how my model is working. There is a dot score from the metrics. So from the sklearn you can get all these particular things. You don't have to do it manually. So dot score is from the sklearn metrics library, in which you can see how your model is fitting. So basically what does this do? It finds the whether x test, whatever the predicted y is here, is approximately equal to y test or not, or is there any misclassification. So your model is giving 93% accuracy here. Okay, so before also I guess there is just a 93%. There is no much improvement using AdaBoost. And always remember guys, so basically boosting algorithm works very well on the big data sets. Since the iris data set is just a shape of 150, that means just a 150 rows, there might be no much difference, but you can see the steps how to work with the big data exactly like this. Okay, so this is about the scores. And next, if you look at the accuracy, that's what the accuracy is, what 93%. Okay, so next, so this is about, now I got 93%. Let us keep this as a benchmark. Now I just want to improve this. This is how exactly you do in the industry. So if you do EDA, then you do some of the pre-processing, you do data engineering, you do feature engineering, you will add the variables, you will remove the variables, finally fit some model. All you need to do is that get the best model to predict the output. Until you get it, you can try a multiple thing. So as I mentioned, I am using the hyperparameter tuning, and I am using the grid search CV. So there are two basic methods. We know that there are two basic methods of hyperparameter tuning. One is the random search CV and one is the grid search CV. So we actually in the industry always prefer to use the grid search CV because random search CV chooses the random hyperparameter values. It might miss some of the values which is actually good than that. So always use the grid search CV when you have the lesser data. Okay. So now I'm going for a grid search cross validation. So there is a parameter grid I want to create. So now let me tell what is the grid search CV. How does your grid search CV works in order to understand how your tuning is working here. So basically what does grid search CV do? What is a grid? Grid is nothing but something like this. Okay. So it has so many values. Finally, how it starts is this algorithm works based on that. So basically it starts with finding the best parameters to your whatever the parameter you have. As I mentioned, there are two major parameters which you should tune in order to get the best result. So one is the n estimators, another one is the learning rate. So what I'll do, I'll just make a list of how many estimators that I want. So I'm giving 100, 200, you can also give 300, 400, etc. Okay, you can give like that. So your grid search CV will find the best parameter. Okay, so it will find the best parameter for n estimators. So n estimators and also learning rate. Okay, that means which it also had the trade-off. First it go and find what it will do is that it will fit all the particular values here for both 100 and 0.001, 200, 0.001. I mean it has a multiple grid combinations. Finally it will give a best n estimator in order to use for the AdaBoost algorithm, and also it will give the value for the learning grade which will fit your model well. So it will choose by itself. There is a grid. By calling the grid search CV, it will choose the best parameters to get the best output in the AdaBoost algorithm. Okay. So this we should always use this particular technique because it is a very helpful technique. It might take a little bit more time. You can see the kernel is busy because it finds the best grid or the best output for the n estimators and the learning rate. Okay. So what exactly it is doing here is, so you can see n estimators. So I am giving the two estimators like 100, 200, like whichever is fine, that is should be fitted. And learning rate, I am giving multiple values for the learning rate. You can give the n range also. So first what am I doing? I am calling the grid search CV. So in the grid search CV classifier, I am giving the AdaBoost classifier and the parameter grid. So I am passing this grid. Basically it takes one classifier and the grid. Okay, that is the two major important arguments or the parameters it will take. So next what I'm fitting the training algorithm. So I'm directly first searching the best estimator and fitting the training and fitting those estimators or the AdaBoost classifier on the training to see the accuracy. Okay. So basically if you look here, then it should predict the X test. So again it should give the score. So I don't see much improvement on the score. Why? Because as I mentioned, since our data is very small, just 150 your boosting algorithms or any type of optimization technique will not work so well. And also this data is very balanced. So there might be no much variance more than that. So what is the meaning of accuracy? Like why are you going to find so much about accuracy? I mean more accuracy in other models. See, if there is something which is unexplained from the first model, you tune it, do some variations and find it in the another model. Okay, so that's what I'm just trying to do. I guess since the data is small, I'm not seeing much improvement, and also since data is well balanced, I don't see much improvement. Okay, that's fine. Let us go on fit another model, maybe just to see accuracy. So accuracy has not improved much since the data is very small. Okay, so it's just 150. And you can see again there is a small misclassification as before. no much improvement from using the AdaBoost Classifier. I hope you're all clear with this. How does AdaBoost Classifier work? It will take the base estimator. I'm using the decision tree, and learning rate is again the hyperparameter which we need to tune in. Okay, so these are the hyperparameter grid I'm giving. Using the grid search CV, I'm finding the best hyperparameter to fit the training. Okay, and there is no much improvement. I hope this is clear. So next up we have is a gradient boosting algorithm. So the gradient boosting algorithm is a second type of the boosting technique, so which we are actually looking into. So next is the gradient boosting. So gradient boosting is a boosting algorithm which focus more on numerical optimization. So it is numerical optimization. Reducing the loss function of any kind of function is called as a numerical optimization, and its objective is to minimize the loss function. Okay, so how it does? So by adding the weak learners using the gradient descent. So here it just passes the weak learners to the next particular model by using the gradient descent method. So what does a gradient descent method do? It will just find the weak learners very quick, since it is an optimization technique, than by providing the more iteration towards the model. So from the AdaBoost, this is a bit faster compared to the AdaBoost, and the result from the gradient descent or the gradient boosting algorithm is much more efficient compared to the AdaBoost. Okay, so this is the improvised version of that. So there it has been assigned with a particular weight and given with the next model. So those steps can be actually reduced by using the gradient boosting. So it will also give you the best output for some of the data. Even when the data is a bit small, you can use the gradient boosting classifier. Okay, so it is bit advanced than the AdaBoost. So why it is called gradient boosting? Since it uses the gradient descent method. So it finds the weak learners by adding the weak learners to the next model by reducing the loss function. And it also uses the gradient descent method. So it is, you can see the method. So it is exactly the sequential method, but at each model, it reduces the loss function by using the gradient descent. Okay. So it will go on reducing until you get should be the loss function which is very minimal or totally equal to 0. So from the sklearn, I'm just importing the gradient boosting classifier here. So I'm giving some of the parameters, and as I mentioned, each optimized or each model here has its own parameters which is need to be optimized in order to just tune on it, or in order to just get the best results out of it. Okay, so here I'm giving some of the default values. So n estimators I'm giving it 100. So depth I'm giving it 2, maximum depth. So that is for the tree based tree that we are using. Learning rate is just 1, I am giving it as 1, and the criterion. So since there is a loss function, you should always have the criteria for the loss functions. There are so many loss functions. Absolute loss functions, you have the squared errors. Okay, so minimum squared errors, RMSE, root mean square errors, etc. So I am using the mean squared error as my criteria since there is a loss function. So next, I'm just providing this boosting classifier as a GC, just to avoid to call this whole function together. So here I'm just explaining the parameters. Again, n estimator is number of the boosting stages to perform. Okay, here number of estimators are the number of base learners you want, or the number of the boosting stages to perform. Then the learning rate. Learning rate shrinks the contribution of each tree by learning rate. So basically there is a trade-off again between. So what should be the learning rate and how many estimators should be there. For these two, again these two are the parameters that you can tune on the hyperparameter. So the criterion, as I mentioned, is a function to measure the quality of the split. That means if the mean square error is more in the first split, then I can say I have to reduce that. So next I'll pass it through that. So using the gradient descent, this is the gradient boosting method, how it works. Then the maximum depth. So it is the maximum depth of the individual regression estimator. Here I am using the classification estimator. The maximum depth limits the number of nodes in the tree. So why this is important? Because let's say you have so much of maximum depth in your base learner. It leads to the higher variance in your data, and again it's a higher computational complexity. So you should always have the depth which is actually less, or you can say with the less particular depth of the tree or the base learner, I should get the best output. Okay, it should be generic. So if you go on making so many rules, when you give the unseen data to it, it will always have the problem with that. So the maximum depth is also one of the criteria for the base learner. Okay, so next what am I doing? I'm going to fit this on the training data set. So next I'm just predicting the output, and also I could see the score. Now you can see how drastically your score has changed. So as I mentioned, it is bit advanced than your AdaBoost. Also it fits well with some of the data which is lesser or the imbalanced data. Okay, so before with the AdaBoost, I just got 93% as the accuracy. So with the gradient boosting, I have improved my accuracy to 96%. Okay. So, and also you can see the misclassification has reduced now. So before it was 2, now you could see it's just 1, and it is classified as the true values here. So all the diagonal elements, you can see it is all the true positives, true negatives. So basically it is the true values. Okay, so this is about the gradient boosting algorithm. So by using it, we can improve our result on the particular data set that we are using. So next, we will see the next effective and the best algorithm in the industry is the XGBoost algorithm. And always remember, XGBoost algorithm is not from the sklearn. XGBoost itself is a different ocean. So they have its own packages. Okay, so it is not developed from the sklearn. It is a different library by its own. Okay, so we are not calling from the sklearn XGboosting. You should call the XGBoost itself. Okay, that means it's a different library we need to import. Why there is something like that? See, by using the XGBoost, it's very important. It has so many features which is advanced than your gradient boosting and advanced than your AdaBoost. Okay, so it has actually features like it uses the imbalanced data well. It has its optimization in the imbalancing. It has its own regularization. It has its own beauty in producing the accuracy really very well. And very importantly, XGBoost works best or the most best when you have the larger amount of the data. Okay, so always keep this in mind. So XGBoost stands for the extreme gradient boosting. So again, it is exactly the gradient boosting. As I mentioned, it reduces the loss function at each split of the data, but mainly it is extreme gradient boosting. So what does extreme means? It has added some of the features. Okay, so which is an optimized distributed gradient boosting algorithm. So which is flexible and accurate. So which is more flexible than your gradient boosting. And also what are the some features of gradient boosting here? So that is extreme gradient boosting. So XGB is an open source library. As I mentioned, it is itself is a own library, and providing the regularizing gradient boosting framework. What is regularizing? By adding some of the values to your loss function to reduce the bias or the variance. It is basically reducing the bias and the variance drastically. Okay, framework for languages, and also it works as a framework for languages like you can use a C++, Java, Python, any type of language, and it works on any system. Okay, so you can use it for Linux, Windows. So, and also one main thing, when you're working with a big data, XGBoost really works well with the parallel computing. Okay, so there is a concept of parallel computing. When you learn the big data, you will learn it, but this algorithm will provide us flexibility in terms of the big data too. So since as I already mentioned, XGBoost has its own library, we need to install it by calling it as the pip3 install XGBoost. So it will help you to install the XGBoost to your Jupyter notebook or the Jupyter terminal or Anaconda terminal basically. So next you can just import the XGBoost as XGB, and you can see which version that you are using. So I'm basically using 1.5.0. This is the version here. So next you have its own parameter. Okay, so I have the parameter as the learning rate, so I'm giving it as 0.1 for now, and the maximum depth as 2, and the n estimators as 1000, and the subsample as 0.7. So we will discuss this. What is subsample and estimators? We already know how many estimators I'm using. Maximum depth we already know. A depth of the tree that we are using, and the learning rate. Basically, I'm giving it as a 0.1. So after fitting, I could see it has fitted. So basically, I'm using this classifier. So from the XGBoost, I'm calling the XGB classifier. So why? Because you also have the regressor. So I don't want regressor since this base model is a decision tree. So I'm calling the XGB classifier, and I'm fitting all the parameters. I'm providing all the arguments inside the bracket, and I'm fitting this XGB. Okay, so basically this XGBoosting classifier on the training data set here. Okay, so once you run this, you can see it has fitted. And let us discuss what are the parameters that we have. N estimators, we already know that is the number of estimators. Learning rate, we already know that learning rate shrinks the contribution tree. Okay, so this is how, at what rate that your particular values or the model should learn. So next is what the subsample. This is something different from other normal models like that we have discussed, gradient boosting or AdaBoost. So subsample ratio of a training instances. So basically it just subsamples from the population. It sample a few data point at each level. So basically I'm taking the subsample as 70% here. So I'm providing it to the particular data or a particular model. So I'm taking 70% as a subsample. Setting it to 0.5 means that XGBoost would randomly sample half of the data to its training to growing trees, and this will prevent overfitting. Okay, so subsampling will occur once in every boosting iteration. See what will happen when does the overfitting happen? So basically when there is a maximum depth of the tree and you have so much to train, so then there is a problem of overfitting. In order to avoid the overfitting, we have extra feature that is subsample, which is related to your XGBoost. So the ratio is basically between the 0 and the 1. Okay, so you have the ratio between 0 and the 1 for this in order to avoid the oversampling. Okay, so you can try it out, like you can give the different subsamples to improvise the result, that you can do it with the hyperparameter tuning. So as we done like before how to do the hyperparameter, we know that. So we can give the particular hyperparameters, which is external parameters that we are providing to fit the model. So your grid search CV will find the best fit or the best hyperparameter or the best parameter to fit the model or the training data. So here I am using this, so I am predicting the score here. Okay, so I need to run this. Okay, so I'm predicting the score here. So I got just 93% as the output. So again, there is no much improvement, but when you take the XG gradient boosting, there is an improvement. Why there is no much improvement there? Since accuracy is still 93% and there is no much improvement in the classification, because XGB basically needs a large amount of the data since it's its own library and it has its own specificality. So in that specificality, it should always be fitting on the large amount of the data. Okay, so this works very well on the big data industry, etc. So from the XGBoost, I am importing the plot importance. Another one main importance of the XGBoost algorithm is that it is not only accuracy oriented, it is also very much interpretable. We all know that there are two types of the models. One is accuracy oriented, just to improve the accuracy and give the accuracy and not worry about which variable is important. Okay, but XGBoost will provide you which variable is exactly important. Okay, so by providing its a particular variable scores or the variable importance value based on its variance. So in the EDA itself, we already have that thought with us. The petal length and the petal width are the two features which is actually important. Let us see when my model is providing the same. If you run this particular line, you can see that. So sepal length is given with a less score. Okay, less importance. Sepal width is given with again the very less importance, but the petal values are given with a higher importance, especially the petal length is given with a 0.58 as a much important. So by using the XGBoost classifier, we can actually have which feature is important. So why this is important? So finally you can tell your stakeholder that this particular variable is important. We can keep these important variables in order to improve our results in future. Okay, so that is very important. By using the XGBoost, we got which variable or which feature is very important. Okay, so and we know that petal measures are very important even in the ED, and your model is also providing the same output. So what about the conclusion? So I'll go through the conclusion. XGBoost is faster algorithm compared to all other algorithms. Why? Because it works on the parallel and the distributed computing, as I mentioned. So if you want to work with the big data on the parallel computing, gradient boosting, AdaBoost will obviously fail because it is parallel computing. It is not a one bit library or not have any such specification, but your XGBoost works really well. Okay, so the XGBoost is developed with both consideration in terms of the system optimization and the principles in the machine learning. So this is important. The goal of this library is to push the extreme of the computation limits of the machines to provide the scalable, portable, and the accurate results or the accurate library. So by now we all understood that we have the first classifier AdaBoost, which we have seen how does the result look like. Next we have gone on with the gradient boosting, which actually upgraded our result a little bit, maybe 0.3%. And next we are fitting up this the XG boosting. So XG boosting is not providing the result, but as I mentioned, in this boosting algorithm, if I want to compare, XGBoost is computationally amazing, and also you can use this in the industry in the parallel computing. Okay, since this data is small, you don't see much differences in the results. Okay, you can also do the hyperparameter even to improvise this result. So I just explained it in just a gradient boosting. You can also implement the same hyperparameter tuning in all other particular algorithms also. So yeah folks, so that's all about the boosting algorithms. By now we are all familiar with how does a boosting algorithm works, which algorithms to use. Based on the data, your algorithms will provide the result. It's not always XGBoost will provide the best result. It's not always AdaBoost will give the less result. It is about the data. It is about the tendency in your data or the variations in your data. But if you want to compare, XGBoost is amazing. Okay, first comes XGBoost, next comes gradient, next comes is your AdaBoost algorithm. So that's all for this video.
Now, we know what bagging is. We know what boosting is. You should be very curious to say, hey, both these cases we're working on the bias and the variance and making sure our models can perform better as one, but are there any differences between bagging and boosting? Well, ladies and gentlemen, I cannot tell you that we cannot have points and discuss the differences between bagging and boosting. It actually completely depends on the circumstances, on the data. It depends on the simulations as well. Because what happens is that bagging and boosting will decrease the variance of a single estimate, because they will take multiple estimates. They combine multiple estimates from multiple models, and there's a very good chance when you do that, 90% of the time your overall variance will dip. And of course, that's a good thing for us, right? So at the end, what happens? The model performance will go up. Model will be performing really well. It is more robust. It is more stable. There's a very good chance when you use concepts such as transfer learning or something where you have the same data, multiple models work on it in a different way. That's when you can take the same trained model to perform well on different data as well, right? So overall, the advantage of bagging and boosting is really high, and when you directly compare it, you have to understand that it varies from situation, it varies from algorithm to algorithm, and more than that, I think the biggest thing it varies is with respect to the data that you're providing, right? Because data, let's be honest, is a million types of data that you can work with, literally, right? So you might be a person who's asking a question right now saying, okay, so how can we measure the performance of a model? Now, to measure the performance of a model, as a machine learning beginner, you would have learned this, right? We would actually split the data into two pieces. One is called as a training data set. The other one is called as a testing data set or as a validation data set. Now, the training data set is a very similar concept of your textbooks in your college and schools, right? You're given certain textbooks, you're asked to learn using those textbooks, and what happens at the end of your academic year? There is an examination, there are multiple semesters and all of that, right? So you have to go there, close your textbook, make sure you recall everything from your memory, what you have learned, and eventually start doing that, right? So if we do not split the data into training and testing data set, I'll tell you what happens. It's a very big blunder that happens actually. So you have provided 100% of the data for your machine learning algorithm to learn. It has learned each and every one of those data points. It knows it thoroughly. So if you start asking questions from it, it is obviously going to give you a 100% accuracy because there is nothing that it has not learned in that data set, right? It knows the in and out of that data set. It's almost like me saying, hey guys, come write an examination, but you can have your textbooks right next to you. So in that case, you really don't have to do any learning at all. You can open your textbook, copy, paste, you're done. Correct? There's no learning happening. When we split it into two pieces, when we say, hey, you learn, put everything in your memory, come back, and eventually, start reproducing from what you have learned. That is when you're trying to validate. That is when you provide brand new data that your machine learning algorithm has never seen in its life before. You're going to use that new data to assess and analyze if your machine learning algorithm is performing the way it should, or if it's misbehaving in any sort, right? So that is when you'll get to know actually, hey, my machine learning model has learned something or not learned something. So it is a very, very important part for you to understand how we measure the performance of a model, right? So it's trained on the training data set, and later we're going to be performing validation, and that's done using a very different data set that's called as the validation data set, right? So you can think about assessing the training accuracy based on the training data. You can have that as a measure, and you can see how good your model actually is by working on using the validation data to fit it across your training data to figure out if your machine learning model has learned something or not, right? That is testing your training accuracy. And when you're talking about validation accuracy, it is same as well, right? Whenever you go on to provide brand new data to a machine learning model that has learned something, it will basically reveal the capability of the model. It will tell you how much of generalization is possible. If you're talking about somewhere like you're analyzing your sales data for the last 1 month or something, wonderful. Once you start providing the data, it learns something. And how much are you sure that your 1 month's data is representative of all the data, sales data that you might have had as a company? Maybe you're a 20-year-old company, right? So how well will your model behave on all of those data? So this is when you will get an idea when you're working on validation data sets. It's for the fact that you can use it to verify how your model would behave if you were to provide more data, very different data, or something like that, right? So we can say the performance of a machine learning model is good, right? So if it can fit your machine learning data well, training data well, and at the same time, it can also predict all of these unknown data points accurately, and that happens through what? Through the validation data set. So ladies and gentlemen, the concept of bagging and boosting, the concept of performance analysis is very, very important. Now let's talk about one or two cases where, let's just say that, if you have a single model which has very low performance, it means that bagging rarely gets a better bias in that situation, right? When you think about it, if your model is low performing, first thing you'll be looking at is its bias and variance, and working with bagging, you usually preferring variance out there, right? So there are situations where your bias can get hurt. But when you're using bagging along with boosting, that's when you can generate a combined model with eventually better bias values, better variance values, right? Because having just single models will bring its own disadvantages, but once you start clubbing them, it's just one disadvantage you'll have to take care about, right? So bagging also has the capability to actually increase the generalization ability. As I just told you previously, you will analyze, you will assess, you will understand how well you can predict the unknown samples as well. So guys, with this, we have come to the end of the course. Thank you so much for watching. To quickly summarize everything we have learned in this course, we started this one out by taking a complete introduction to understand what important terms such as bias and variance are. We took a lot of examples to understand what bias is, what variance is, what weights are, how these weights play such an important role, and eventually we worked ourselves into understanding ensemble methods. We understood what ensemble methods are, how they work, why we require it, and in fact even why they work the way they do, right? We took a look at the two types, parallel and sequential. We understood a couple of examples with parallel, we understood a couple of examples of sequential, and as soon as we did this, we dive right into the topic of understanding what boosting is. Right now, I am sure you would understand that if we had not covered those ensemble methods before diving right into boosting, it would be extremely difficult for you guys to get a complete picture, right? So we had to discuss boosting, a good amount of examples there as well. We compared bagging and boosting, and we realized that it's not really a very simple and straightforward comparison as you might have thought. We gained a lot of insight from that. We eventually went right to Python. We did a very simple example.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.